Hello there, I am Tan Chao Xiang, and today I will be presenting to you my project on sensor fusion-based vehicle detection using camera and radar in smart traffic management systems, which designed for smarter and more adaptive traffic monitoring. In this presentation, I will show how sensor fusion can offer a more reliable, flexible, and future-ready alternative for traffic monitoring. Let us begin with how traffic monitoring is conventionally done today. One of the most widely used methods is the inductive load detectors, which is embedded directly beneath the road surface. While effective, this approach has several key limitations. First, installation and maintenance are highly intrusive. Roads must be excavated, causing traffic disruptions and long-term infrastructure damage. Second, that inductive loads only detects vehicles at fixed positions, providing very limited spatial awareness. Finally, these systems lack adaptivity. As traffic patterns become more dynamic and complex, point-based detection is no longer sufficient. These limitations motivate the needs for a non-intrusive and more intelligent traffic sensing solutions. To address these limitations, vision-based systems such as cameras are increasingly explored in traffic monitoring. Camera-based systems provide rich visual information such as vehicle shape, size, and appearance, making them effective for classifications and scene understanding. However, their performance degrades under poor lighting and occlusions. Radar sensors, on the other hand, offer strong advantage in adverse conditions. They directly measure range and velocity, and they operate well in darkness and rain. Nevertheless, radar lacks visual contact and may suffer from electromagnetic interference or multipath effects, leading to noisy or duplicated detections. This leads to a key question: what if we could combine the strength of both sensors while minimizing their individual weaknesses? To address these challenges, we propose a non-intrusive camera radar fusion systems for vehicle detection and tracking. By combining camera and radar sensings, the system gains redundancy, robustness, and richer perceptions. Even when one sensor becomes unreliable, the few systems can continue tracking vehicles, making it suitable for real-world traffic environment. The innovation here lies not in using new hardware, but in designing an intelligent fusion and association framework that integrates detection, tracking, and lifecycle management across sensors. Now, let me briefly explain how the fusion framework works. The proposed system adopts a decision-level fusion approach. This means each sensing modality performs independent object detection and tracking, optimized for its strength. To align information from different sensors, the systems perform temporal synchronization using linear interpolation to align radar and camera timestamps. Spatial alignment is achieved through homographic projections, mapping camera detections into radar cloud plane. This allows radar and camera detections to be represented in a common reference frame. Finally, in the fusion engine, we use the Hungarian algorithm for cross-sensor association and a Kalman filter for estimates the fused vehicle states over time, producing smooth and consistent vehicle tracks. This architecture keeps the system modular, scalable, and robust. Rather than relying on a single association steps, the fusion engine uses a multi-stage association strategy. First, ID locking preserves non-camera radar association across frames. Next, cost-based associations resolve unmatched detection using spatial and motion consistencies. Camera-only and radar-only tracks are then handled explicitly before final tracks confirmations. This stage approach significantly reduces identity fragmentation, false associations, and track instability, particularly in complex or partially observed scenarios. Now that the fusion process is defined, this video shows the real-world output of the proposed camera radar fusion frameworks. Each track ID represents a fused vehicle track, and the counter at the top right shows continuous vehicle counting based on the stable fusion results. This demonstrates how fusion enables reliable tracking beyond single sensor limitations. Next, I will show how this fusion framework maintains track continuity even when one sensor temporarily fails. This example highlights one of the key strengths of sensor fusions: robustness to sensor dropouts. In this example, we observe a temporary camera failure due to occlusions. While visual detections become unavailable, radar-based range detections remain active. Through fusion, track continuity is preserved, allowing the systems to maintain a reliable vehicle tracking even when one sensor fails. This redundancy is critical for real-world deployment where sensors' reliability cannot always be guaranteed. To quantitatively evaluate performance, we compare camera-only, radar-only, and fuse tracking results across key metrics such as precision, recall, ID switches, and multi-object tracking accuracy. The fusion approach consistently outperforms single sensor methods. This highlights that fusion not only improves robustness but also enhances overall tracking accuracy and stability. This fusion framework has strong potential across multiple traffic-related applications. In intelligent transportation systems, it can serve as a perception module for future connected and automated traffic platforms. At smart intersections, it enables accurate vehicle tracking for adaptive signal control. Additionally, it also supports traffic monitoring and analysis such as flow estimations, congestion detections, and also vehicle behavior assessments. Beyond technical performance, this project also delivers meaningful social and environmental impacts. By improving traffic awareness, the systems also supports smoother traffic flows and reduced congestions. Its non-intrusive deployment also avoids road excavations, minimizing disruptions, and also maintenance costs. Ultimately, better traffic efficiency also leads to lower fuel consumptions and reduced carbon emissions, contributing to more sustainable urban mobility. In summary, this project demonstrates how camera radar sensor fusion can provide a robust, adaptive, and future-ready solutions for traffic monitoring. By addressing the limitation of conventional systems and single sensor approaches, the proposed framework supports smarter and more sustainable transportation infrastructure. Thank you for your time and attention.